Now let's first think about the wall test. So the wall test is a test you learned a while ago, and it can be applied to maximum likelihood estimation. So this is the model in which you learn the wall test. Let's say you have n IID samples following some distribution p theta with some smoothness guarantees on theta, where theta lives in Rd. And you have IID samples. And then under some regularity assumptions, the maximum likelihood estimator, theta hat for theta, behaves nicely. And in what sense does it behave nicely? If we want to test whether theta is actually equal to some theta naught or not, then we can do this via a test statistic that looks like this. You take n, and then the vector matrix vector product theta hat minus theta naught I of theta hat times theta hat minus theta naught, where I is the information matrix. So as a reminder, this could be defined under regularity assumptions again as minus the expectation of the second derivative of the log likelihood for one sample. OK, and then the important part, OK, and this is only test statistic, and how do you cut off? You cut off via this observation that asymptotically, this statistic under H0 goes to a chi-squared distribution with d degrees of freedom, d being the dimensionality here. OK, now we want to apply this in our case, and we do have a maximum likelihood estimator that we could work with. The only problem is that the test I'm interested in fixes or singles out one particular coordinate of your parameter vector beta, and this one does not. So and I do not want to impose values on all the other coordinates of beta. I just want to say they are fine with whatever they are. I'm only interested in, for example, is the first coordinate 0 or not? And we can actually do something similar, and we will still call this a wall test by unraveling the steps that led to the proof of the wall test. So let me review those steps for you quickly. How do we do this? This was essentially based on the theorem for the MLE you had in class that establishes asymptotic normality. Yeah, and by the way, the two tests I'm going to show you, wall test and likelihood ratio test, they're both asymptotic tests. So the theorem for the MLE told you that if you take theta hat, so essentially this is some kind of central limit theorem, minus theta, and let's call theta the true parameter. You scale it by square root n, and and you just leave it like this. Then this goes to a normal distribution in distribution that is centered. And as a covariance matrix, it has the information matrix at theta inverse. So you take this matrix, and it needs to be invertible. That's essentially corollary from the assumptions we made on the MLE for this theorem to hold. And then you have asymptotic normality. And from there, we've seen this. I can construct a pivot. In particular, you could, if you wanted to, so the problem is if this is a d-dimensional thing, then we need to think about how do we get one number that allows us to cut off. And one way is by looking at the Euclidean norm of this vector, and Euclidean norm of this vector, but weighted by the I here to obtain a chi-squared distribution. So as a corollary, essentially, if I take almost this product up here, then I get a chi-square distribution with d degrees of freedom. And this just comes from the fact that this I in the middle essentially reverses the covariance here, or it whitens. Some people call this whitening, because it makes the variable square root I, if I take a matrix square root, times theta hat minus theta, look like a standard normal random variable. And then I'm just looking at the Euclidean norm squared of a standard normal variable. This is a chi-square distribution. Cool. And there's one problem. I don't know. So theta is kind of fine. Theta I will replace for my test by theta naught. But I of theta is not so cool because I don't know the underlying theta. So by Slutsky's theorem, I can replace this asymptotically by the information at the estimator theta hat, because theta hat is consistent. OK, and the test that you get, psi would be, just cut off Tn, where Tn has, Tn I wrote down with theta naught at the 1 minus alpha quantile of the corresponding chi-square distribution. OK, so and now what we're going to do is essentially we're going right there at the first step. We can still apply the theorem for the maximum likelihood estimator. We will still have asymptotic normality like this. And then what we're interested in is essentially only the coordinate beta j. So we are just going to try and figure out what is the marginal variance. So if I have joint asymptotic normality, I can deduce asymptotic normality just for the coordinate beta j. And then the only thing I need to figure out what is its asymptotic variance. And the asymptotic variance is just given by the diagonal element of I. All right, so here we will still have square root beta hat minus beta, the underlying beta, the true beta in our model, goes in distribution by the same theorem to a normal distribution with the information here, inverse. With one caveat, of course, in this expectation, I also have an expectation given my modeling assumptions over the xi's, but that's kind of fine. We will need an additional estimator at the end of the day to get around this, because we cannot just simply calculate I if the distribution of the xi is not known. But let's gloss over that fact for a moment. OK, so what does that mean for beta j? That means square root n beta j hat minus beta j in distribution. I'm just marginalizing this one out, goes to 0. And the variance of beta j can be found within this big matrix as the diagonal element, as I of beta inverse, and then the jth diagonal element. Right? Cool, and that's almost it. So now the only thing I have to do is, again, normalize by this. And then the only problem that remains is I have to get my hands on an estimate of I, because I is not explicitly known here for the distribution of the xi is not known. And for this, I would just suggest using, for example, this. This is defined as an expectation. So let's just take an average. So I would say that we have an estimate of the information by averaging out the corresponding second derivatives of the likelihood, the Hessians. Well, so Hessians are, Hessians, because then I need to invert it. So let me write L1. And a minus sign. And then I need to also estimate beta, and this is another subtlety that I'm glossing over here. So essentially, I know that an expression like this for IID data will converge for fixed beta by the law of large numbers. But what I need to know here is this quantity that I want to use as an easy plug-in estimator. So I want to first estimate the function, the matrix-valued function that is the information, and then I'm going to plug in another estimate for the true underlying parameter. How does this thing behave? And this would be theoretically justified by something like a uniform law of large numbers. That says that if I plug in a consistent estimator into a nice continuous function, then this will also be consistent as n goes to infinity in a nice function that is pointwise consistent and has some continuity properties in terms of beta. Let's not worry about this too much, and let's just assume that this thing in probability will go to I of beta at the end of the day. And then I can plug this in and make a, if I want, make a chi-squared distribution out of it by squaring it. And then I will have that n times beta j hat minus beta j naught squared divided by the variance, which has another inverse. So I hat beta hat inverse matrix, and then the jth element goes in distribution by Slutsky's theorem again to a chi-squared, and now I have a one-dimensional parameter. I started with a one-dimensional normal distribution, so it's going to be a chi-squared distribution with 1 degree of freedom. So let's write this down. So this is going to be my test statistic then. Let's call it TNW, W for Wald. And let's, right. So I'm looking at how close is the estimated output to the one that I think is the true one, or that I want to disprove from being the true one. And I look at this. And then, of course, if I know that I have a chi-squared distribution, my decision rule is going to be reject if the Wald statistic is larger than the chi-squared quantile Q alpha of a chi-squared distribution, which you probably cannot read here. OK. And now the only thing that remains to maybe worry about is what actually does this thing look like? You already calculated the second derivative here. You already calculated in class, but I want to go through the calculation again just to make sure that we're on the same page about this. And particularly, I'm going to reuse it when thinking a little bit about the power of this test. So and just to repeat, so what? Oh, I forgot to square it here. Just to repeat what I did, we are essentially just using the theorem for the MLE, and we know that our MLE will be asymptotically normal. And then I just extract what this means, what this being asymptotically normal means for the jth coordinate. And then I standardize by something, and I get a chi-squared distribution by Slotsky. And then I have nuisance parameters that I'm getting rid of via plug-in estimator. And I'm glossing over some of the details of why this plug-in estimator is actually consistent. And now I just want to spend a little bit more time on the board thinking about what this plug-in estimator looks like.